into the details of process control system design, we need to highlight the idea of the dynamic behavior of processes. It is very important to analyze the process dynamics in order to have a thorough picture about its behavior and reaction against different inputs. Basically, if we have a process, let's say we have a process with a certain transfer function, we will call it G. This process is affected by inputs and it will produce outputs. Let's focus on the simplest case where we have a single input U and a single output Y. Now, if this U changes in a certain manner, let's say that we have U suddenly changing from one value to another value. We call this a step function. Then we need to know how will the Y, the output of the process, will be affected based on the effect of U. So studying the effect of the input U on the output with respect to time is called the dynamics of processes. Now, these inputs can be very complicated. However, for the case of suitability for analysis, we will study simple inputs that can simplify the different excitations that can happen in a daily life operation of a process. These inputs will represent the type of changes that occur in the plants, and they will be easily to be manipulated mathematically. So we will study now different types of inputs, and we'll start with the simplest and the most used type of excitation for the input, which is the step change or step input. Now, step input is actually a sudden change in the process variable, the input process variable, at a certain time. And this can be represented in many cases during the operation of the process. For example, opening or closing a valve on a pipeline. For example, increasing the rotor speed in a tank, increasing the heat load in a certain heat exchanger or a reactor. These changes, all these changes will happen in a sudden manner at a certain time and raise the input from one value to another. The general form of the input, this step change input of size M, the general form, we call it Y of S, U of S, and it goes like at a certain time, we will start at time is equal to 0. So the value of the input at time 0 changes from one value to another. So before 0, its value is 0, and then suddenly jumps to another value and stays at this value. The size of this change is M. So this is T, and this is U of S. So this is the form of the change using the step change. And it occurs at time 0. There are, of course, special cases. The case in which M is equal to 1, we call it a unit step change. And these are different examples. Reactor feedstock is suddenly switched from one supply to another, causing sudden changes in feed concentration, flow, etc. Now let's take an example on the step change input. For example, here we have the heat input to a stirred tank reactor heating a system is suddenly changed from one value, 8,000, to another value, 10,000 kilocalorie per hour. This is done by changing the electrical signal to the heater. So actually, the time domain representation of the heating load of the heater can be represented as Q is equal to 8,000, which is the value at steady state, plus the value with changes with the step change, 2,000, which is the difference between 10,000 and 8,000, 2,000 times the step change U. Okay. Now, it is also beneficial to write the equation in perturbation form. So in perturbation form, the Q prime is equal to Q minus Q steady state. The Q steady state is this. This is the Q steady state. So at the end, we will have the 2000 times U of t. And in Laplace, since this function contains a constant, here it is 2000, the constant, the Laplace of the constant is simply m divided by s. So this is the Laplace representation of the step change. Here it is represented in terms of a graph. At time before t is equal to 0, the value of the heat load is 8,000 kilocalorie per hour, and suddenly at t is equal to 0, it changed to the next value, which is 10,000. The difference between the two is the m. M here is equal to 2,000 kilocalorie per hour. So this is an example that represents a step change in an input for a simple process. Now, the next type of input is called the ramp function, or the ramp input. In the ramp input, the feed to a process is changed gradually, linearly, at a constant slope. So the process will be at a certain value, and suddenly at a certain time, it starts changing gradually with a certain slope. So this is called ramping. Okay, it's very important to know the rate of change of this input. To represent this mathematically, the change will be U of R. We will call it U of R. A is equal to A of t at time is greater than 0, where A is the slope of the ramp function. So actually this is the slope, A, multiplied by time, t. Now it's very important to differentiate between the step change where it changes suddenly, and the ramp. Okay, and sometimes if the time of change is very short, we can represent the ramp function as a step change. Example for ramp changes: changing, for example, feed composition for a reactor in a gradual way. Changing the heat, the change in the heat exchanger fouling. Fouling process, as you know, happens gradually and takes time due to the deposition of scales on the internal sides of the tube. And this happens with time and affects the heat transfer characteristics of the heat exchanger. The catalyst activity, which will decay by time gradually. The ambient temperature changes gradually throughout the day. These are different examples of the ramp input. Another common type of change is the rectangular pulse. We have studied this before, and actually it is a combination of two steps, one positive step and one negative step. This kind of change represents a brief change in the process input. So the change occurs as a step at time 0. At time 0, it goes to another value. We will call it h here. And then at another time, it will go down to the same value. And this represents a square rectangular pulse. Mathematically, this is represented as 0 for time less than 0 and time greater than tw. Tw is this point. And in between 0 and tw, its value is H. Examples of such inputs, the reactor feed is shut off for 1 hour. So see, the change here has been done for a specific period of time, 1 hour. Okay. The fuel gas supply to a furnace is briefly interrupted. Briefly, which means limited amount of time. So these are examples of rectangular pulses. The previously mentioned inputs, the step, the ramp, and the rectangular pulse, are the most common process inputs, and we will try our best to restrict ourselves using these 3 types of inputs. But there are other types of inputs that are available but not very frequently happening. An example of such an input is the sinusoidal input. Here the process input goes in a periodic manner, cyclic manner, okay, and this can be represented using a trigonometric function. So its value is 0 before the time is 0. Let me represent this graphically. So if we have the time scale, so this is time scale t, and this is u of s. Okay, let me change the color. Right, so at time 0 there is no change in the process, and suddenly at a certain time it starts going in a sinusoidal way, periodic way, and so on. Okay, this sine wave has a certain amplitude. This is the amplitude, we will call it A, and it has a certain frequency that depends on the period. This is the period. This is the period, but from the period we can calculate the frequency omega. Okay, angular frequency. Examples of such variation: the 24 hours variation in cooling water temperature. It starts at a certain temperature and it goes in a cyclic manner throughout the day. So at night the temperature is cold, and then as the sun rises it goes up, it reaches a maximum, then goes down, and so on. This is a cyclic way of change of temperature. The electrical noise in electricity and the 60 Hertz electricity also goes in a sine wave manner. Another also type of input is the impulse input, which is represented by the Greek letter sigma. It represents a short change in the input, short life change in the input. If you remember the example we took before in the previous chapter for the operator throwing a drum of liquid into a tank. This change happened in a very short time that can be approximated as 0 period of time. Other examples of such input: the electrical noise spike in a thermocouple reading. The thermocouple reads the temperature, and this reading will not happen smoothly. Like in books we say something like this, but in reality this change contains noise, and because of this noise the temperature reading will not be like this, so it will be something like this. So you can see now that the change happens in spikes. These spikes can be approximated as individual impulses. The injection of a tracer dye. Also, in some kind of mass transfer analysis, we may like to inject a tracer. So if we have let's say a reactor with a feed here and the output here. So to study the mass transfer characteristics, we inject a tracer into the feed and monitor its concentration in the output. Okay, this injection process into the feed happens in a very short time, so we can approximate that as an impulse. And the impulse, using impulse in our analysis will simplify the analysis because of the fact that the Laplace transform of the impulse is equal to 1. So the impulse in Laplace is equal to 1. And when you multiply any transfer function with the impulse, you are multiplying actually by 1. When it is possible, we can easily approximate complicated type of functions with series of impulses to simplify the analysis. Now let's see the application of the previously mentioned inputs on studying the dynamics of processes. We will start with our favorable process, the simplest process, the simplest tank system. So we have analyzed this system before, and we found that the transfer function, which is the relation between the output and the input, is simply k over tau s plus 1. Okay, so the output for the tank was the level, and the input for the tank was the Qn. Qn is the input, and H is the level. And this was the shape of the transfer function that we've got from solving the differential equation. K is called the steady state gain, and tau is called the time constant. So if we assume an input U of s in the form of a step change, so basically what we will be doing is that this valve, we will excite it in a step way. So suddenly we open it and raise the flow rate in to the tank from one value to another value. The size of this change is m. This is the size of the change. So basically we will be having this kind of input. U of t is equal to m, or in Laplace domain U of s is equal to m over s. So substituting this into this equation and separating y will give us this form of Laplace expression. And then if we want to find the way in which y changes with time, of course q now, or the level will change in a dynamic way. To know how does this level, which is y here, changes with time, we need to inverse Laplace this Laplace expression. We have also done this some time ago, and we've got the final form for the level, the change in the level as a function of time. This is an exponential growth function. It changes from 0 to a value of km. So the km here, you know, k, what is k and what is m? K, we said that it's the steady state gain, and m is the size of the input. The multiplication of the two will represent the final steady state value of the change. This value here is km. And this y changes from a value of 0 exponentially increasing until it reaches a final steady state value of km. Okay. Now, changing the value of tau, this function now changes due to two factors, the k and the tau. Changing the value of tau, as you can see, this figure, the blue line, represents the dynamics with tau is equal to 10 seconds. However, if we reduce the tau to 1 second, you can see now the graph responds faster. So reducing the time constant as tau goes down, reduces, what happens is that the process becomes faster response or faster dynamics. Reducing the tau will increase will make the process response faster, and increasing the tau will make the process response slower. So this tau actually represents the speed at which the process responds to the two inputs changes. The tau, let me write here, tau represents the speed of response. Small values means faster response. Large values means slower response. The previous example was regarding a first order process, and we said a first order because the order of the denominator for the transfer function of the process is a first order polynomial. Now there are other types of processes in which it does not go for a new steady state when excited, and these processes we call them integrating processes. So these integrating processes, or integrator for short, have the transfer function of k over s. If you remember, this is different than the first order process where we don't have a tau here. And actually this is not a steady state gain anymore because it doesn't have a steady state gain. It's a constant. And if we assume a step change input of size m, so if we assume that this u of s is equal to m over s, substitute this here, we will get y of s is equal to km over s squared, and if we take the inverse Laplace for that, we get the final time domain form of the dynamics of the y with respect to t. Now km here is not the steady state value as in the first order process. So actually it represents the slope of change. This kind of process will behave if we have an input. Let's draw the process. And now we have an input. Let's say that we have a step change input. The output, this is u, and this is the process transfer function. The output of the process will be having a kind of ramp form with a slope of km. This slope is km. So this is y of s. Now you may wonder what kind of process can be an integrating process. If we go back to our tank system and we install a pump on the outlet of the tank. When we install a pump, that means we have fixed the output Q. The output from the pump has a fixed flow rate. Okay, we can change it, but once changed, it will stay fixed. It is not a function of h anymore, as in the case where we don't have a pump. So for that case, this Q is fixed now, which means that when we analyze the system, this is the differential equation, and when we analyze the system, its perturbation value will be equal to 0. Why? Because now the Q prime of S will be equal to the value at steady state minus sorry, the value at any time, which is the steady state value, minus the steady state value, which is equal to 0. Okay, so this will make this part 0, and continuing the analysis, we will end up with a transfer function of this form, 1 over AS, and as you can see here, there is no gain in the in the process, or we can say that the 1 here represents the K, and K is not the process gain, because the form of the level now will be something like this. It's either going up to infinity or going down to infinity without a steady state, and this is a kind of integrating process. Similarly, this can happen when we change the pressure inside a vessel, and this pressure keeps changing and increasing without stopping. Another common system is the second order system, where we have the standard form of a quadratic polynomial in the denominator. And if you remember, we took this before in the case of two connected tanks, the interacting and the non-interacting way of connecting the tanks. So the relation was between the feed flow rate to the first tank, Q in, and the level and the, the flow rate in the outlet stream of the second tank. And this was a second order polynomial in the denominator, where we have the tau and zeta. The tau is called the time constant, which has units of time, and the zeta, we will call it the damping coefficient, and it's dimensionless. It may have values negative or positive, and it represents the dynamics of a second order system. The K is the steady state gain. So since there is a steady state gain, this means that this process is a stable process. It will reach a certain new steady state when excited by a certain input. Sometimes we divide the numerator and the denominator by tau squared, and then we can put the equation in this form, which is very common in the electrical engineering process control systems. They call the 1 over tau, they call it the natural frequency, and the transfer function then is written in this way. So now we need to study the dynamics of the second order process. Will it be similar to the first order process, where we have a exponential growth in the output due to step change in the input? Let's see. Actually, the dynamics of a second order process will all depend on the value of the parameter zeta, the damping coefficient. Depending on its value, we will see different forms of the dynamics. So now we have a more complicated system than the first order. So if we have a positive zeta greater than 1, then we call this an overdamped system. And in that case, the denominator, or the roots of the characteristic polynomial, are real and not equal. If the zeta is equal to 1, we call this critically damped, and the roots will be real and equal. If zeta is between 0 and 1, we will call this an underdamped system, where we have the roots of the characteristic polynomial complex and complex conjugates with negative real parts. The critically stable response happens when the zeta is equal to 0, where we have complex roots of the characteristic polynomial, and when the zeta is less than 0, the process will be unstable and it will not reach a steady state, and this happens when the roots are complex conjugates with positive real parts. The denominator, don't forget, I always mention the characteristic polynomial. This is the denominator of the transfer function, the tau squared, s squared plus 2 zeta tau s plus 1. This is called the characteristic polynomial. Now let's see how do they look like, how do each one of these responses look like graphically. So we will start by analyzing the change or the dynamics of the second order system due to a step change in the input. So now we have multiplied the transfer function by the step change transfer function. This is the transfer function of the second order system. Multiplying the two will give us the output y. Now the quadratic term in the denominator, this quadratic term can be factored into two terms. We're having these roots SA and SB. These roots will have these forms in terms of zeta and tau. And then we can write the equation, this equation, we can write it in a factored form. Now solving the previous equations will reveal different values for the roots SA and SB depending on the value of zeta. So the values of SA and B will change depending on the value of zeta, and as the value of zeta, definitely the solution will change. Now let's look at this graph. The graph represents the solution of the previous equation using different cases. The case of zeta greater than 1, the overdamped, you can see that it is increasing in an exponential manner. As the zeta becomes 0, the curve becomes very similar to the first order response. Still it is increasing exponential. And as the zeta becomes less than 1, we can see that this red line, a small overshoot over the steady state value. Remember that this is the steady state value. So here we will start to see an overshoot. It's the case of an underdamped system where the zeta is between the 0 and 1. And as we reduce the zeta, this overshoot becomes larger and larger and larger. Now next we will have a zeta of 0. When the zeta is 0, the curve will become sine wave. Exactly sine wave with constant amplitude. As the zeta becomes less than 0, the curve starts to go crazy and go to infinity, unstable. Now, if we look at the solutions for specific cases, 3 cases we will take. The case of an underdamped system where we have zeta between 0 and 1. This is the solution, and you can see easily here that it involves the sine and the cosine, which means that the curve will be oscillatory, a periodic type of curve. These are the curves here resembled by the zeta is equal to 0.1, and then the zeta is equal to 0.25, the zeta is equal to 0.75, okay? And these are the different cases of the underdamped system, oscillatory responses. For the second case, the critically damped, when we have a zeta is equal to 1, exactly, this is the green line here, this is the curve of critically damped response, and we can see the solution that does not contain a sine and cosine function, and that's why it's not periodic. And it is very similar to the first order response in terms of shape or form, and that's why the graph here represents very similar behavior to the first order system. So when the process, the second order process, is critically damped, then its response will be very similar to a first order process. This is a very specific case. The last case, when the zeta is greater than 1 and we have an overdamped system, this is the case represented by the first graph from below here, the blue line. And you can see that the increase is not oscillatory. If you look at the solution does not contain cosine and sine. However, it contains the cosine hyperbolic and sine hyperbolic. These are non-oscillatory functions, and that's why the response or the dynamics will not be oscillatory, but it will be damped. And that's why they are called over-damped. Damped means that the response is slowed down. So this response is slower than this response. And that's why they call it over-damped response. Then we can put general remarks regarding the different cases of a second order process. The remarks are as follows. First of all, when the zeta is less than 1, the response will be oscillatory and it will contain an overshoot. So this happens only when the zeta is less than 1. When the zeta is greater than 1, the process will be responding slowly, sluggishly. So having high positive value for zeta means that the process response is slow. Now the fastest response without overshoot is the case of the critically damped process where zeta is equal to 1. So if we want to have a second order process response similar to a first order response, we have to have the zeta is equal to 1. Now, as you saw that there are different solutions for the second order system depending on the value of zeta. And there should be a way to describe the responses, all these responses, in a more generalized form. So that's why we come to this point to put performance characteristics for the dynamics of a second order process under the effect of a step response in the input. We will take the underdamped case for the zeta is between 0 and 1. So as you see, this red line represents the general form of a second order process. Remove this. Okay. So this is the dynamics of a second order underdamped system. Now we will put some dimensions for the different parts of the curve. We will call this distance from 0 to the steady state value as B, and the distance from the steady state value to the highest first peak is A. The second peak will be called C, the height of the second peak. The difference between the location of the second peak and the first peak, this difference will be called P. And you can see that the response becomes almost at steady state after some time. We will call this time Ts. Now we will define some characteristics. We will call the overshoot as the ratio of A to B. So if you want to know how much is the overshoot, you just measure A and B and calculate the value. Of course, we don't want high overshoot in our response for the process because it will deviate away from the steady state value. The decay ratio is the ratio between C and A. We also want the decay of the overshoot fast. So this will be represented by the ratio C over A. The rise time, the TR, is the time needed for this curve to reach the first steady state value. So when it crosses the steady state value, we calculate the TR. The time to first peak, this is the first peak, and the time to the first peak, this time down, TP, can be also calculated. The settling time, it is this time, it is the time needed to reach the steady state value. However, since we will not be able to decide exactly when this will happen, so we will decide a band between which we will regard this as a steady state value. This band is located between 0.95 B, this is B, and 1.05 B. So if the curve reaches a location in between these 2 points, then we say that we have reached the settling time, and we measure the TS. And of course, P is the period of oscillation. These different characteristics will enable us to judge about the different properties of the dynamics of a second order system. To describe all these characteristics, these are the different definitions of the characteristics, starting with the rise time. The rise time, TR, is the time the process output takes to first reach the new steady state value. Now, in some textbooks, there is another definition, which is the time the process takes to rise from 10 to 90% of the step size. In our analysis, we will regard the first definition, unless it is mentioned in the question. Time for first peak, TP, is the time required for the output to reach its first maximum value. Settling time is defined as the time required for the process output to reach and remain inside a band whose width is between plus or minus 5% of the total change in Y. The term 95 response time sometimes is used to refer to this case, because now 95 represents the lower limit of this band. Also, values of plus or minus 1 and plus or minus 2 sometimes are used in other textbooks, but in our textbook we will regard the plus or minus 5%. The overshoot definition, the decay ratio definition, and the period of oscillation definition. To enable us do conversion and calculation of other characteristics from some of these, we have came up with relations or expressions for some of these characteristics. For example, the time for the first peak, tau p, Tp, is equal to pi tau divided by the square root of 1 minus zeta squared. The overshoot can be calculated as the exponential of minus pi zeta over the square root of 1 minus zeta squared. The decay ratio is the exponential of minus 2 pi zeta divided by the square root of 1 minus zeta squared, or it is equal to the overshoot squared. The period of oscillation is calculated as 2 pi tau divided by the square root of 1 minus zeta squared. Using these relations will enable us to find other characteristics from known parameters for the transfer function. So in other words, if I know the tau and zeta, I can calculate the time for the first peak. Similarly, the overshoot, the decay ratio, and the period of oscillation. So the most important thing is to know the transfer function. Once I know the transfer function, I can calculate all these characteristics. And this brings us to a very important thing here. If I know the zeta, I can know how does the process behaves, and I can know what type of response is it. Is it overdamped, critically damped, underdamped, and I decide about its dynamics. Now let's take an example and see how can we deal with the dynamics of a second order system. Here we have a CSTR equipped with a cooling jacket to remove the heat generated by the reaction, and there is a controller which is used to regulate the coolant flow rate so that to keep the temperature inside the reactor reasonably constant. Now this controller has been designed or tuned, we will take this later in the future, in a way to keep the response of the temperature inside the reactor as an underdamped second order system. And this can be done by the analysis of the feed flow rate or the coolant temperature changes. So there are a few questions related to the system. The first question, the feed flow rate to the reactor changes suddenly from 0.4 to 0.5 kilogram per second. This is the feed flow rate to the reactor. And the temperature of the reactor content in it was at 100, changes to 102. So what is the gain of the transfer function? K. What is K? Of course, under the feedback control, which relates, as you know, the changes in the reactor temperature to the changes in the feed flow rate. Now, looking at the dynamics of the process, this is the dynamics of the process. You can see clearly it is an underdamped system. The system, or the temperature of the reactor increased. At time zero, it was 100, and it reached the final, the first peak at 102.5, and then it oscillated until it reached the steady state value of 102. Here it says that the input to the process changed from 0.4 to 0.5. So this is the input change. And the output, this is the output of the process, it changed from 100 to 102. This is the steady state value. So K, which is the process gain, is defined as the change of the output. This is the change of the output, 102 divided by 100, divided by the change in the input. And the change in the input is this. So we can calculate K easily now. K is delta Y over delta U, which is delta T over delta F, the flow rate. So 102 minus 100 divided by 0.45 minus 0.4, this is equal to 20. We need to be very careful in stating the units. The numerator has temperature unit, and the denominator having mass flow rate unit. So we have calculated the gain from the response of the process. The second part of the question is, the operator notes that the resulting response is slightly oscillatory with a maxima estimated at 102.5. This is the maximum point. This is the peak of the first, this is the tip of the first peak. So this is the one, and the another maxima at 102.03125 degrees centigrade, occurring at these different times. So this is the time for the first peak, this is the time for the second peak. And you can see that the first peak is higher than the second peak. What is the complete process transfer function? Remember that we have calculated the process gain, the K. Now to know the complete transfer function, first of all, let me write the transfer function. It is the G of S, the transfer function, which is the ratio of the output of the process, which is the temperature here, divided by the input of the process, which is the flow rate. I think it's called F node. And this has a second order form. So it's K, which we have found in the previous part, divided by tau squared, S squared, plus 2 zeta tau S plus 1. So this is the form of the transfer function. We have already found this. Done. Now we need to find the tau, and we need to find the zeta in order to complete the definition of the transfer function. So looking at the information we have, this is the temperature for the first peak, the highest tip, and this is the one for the second peak, and these are their times. So from the times we can find the period, because the period is the difference of the times of two successive peaks. And from the period we can do other calculations. Now the overshoot, as you know, let me remove this. Okay, the overshoot is defined as minus pi zeta over the square root of 1 minus zeta squared. And this overshoot can be calculated from the difference of these two temperatures. Okay. And once I know the difference of these temperature, I will divide it by the difference from the initial point to the steady state value. Let me remind you that the curve here we are talking about is something like this, and we are looking at the B and the A. So the overshoot is the A. This is equal to A over B, and A is the difference of the temperatures, and the temperatures here, I mean this temperature minus this temperature. So this temperature is the 102.5, and this temperature is the steady state value. This is the steady state value. Next, the B is the difference between the steady state value and the starting of the response. So 102 minus 100, this gives us 0.25. Once we know the overshoot, I can rephrase the equation to give me the zeta from the overshoot. Then I can calculate it as almost 0.4. Now I know the zeta, I still need to know the tau. Tau can be calculated from the period of oscillation, which is the difference between these two peaks times. So the period, if known, I can calculate the tau because now I know this zeta. The period is the difference, as I said, and substituting this in this equation will give us the value of the tau. So now I have the zeta, and now I have the tau. Previously I've calculated the k, so I can put the transfer function as 20, the k, divided by 90,000, which is the tau squared, s squared plus 2 times zeta times tau. It becomes 240 seconds plus 1. So this gave us the transfer function of the process. Again, I want to remind you that we were able to get the transfer function of the process not from the mathematical modeling of the process. We have used the dynamic response, which is usually an experimental one, and from the characteristics of these dynamics, which are the overshoot and the period, we were able to calculate the tau and the zeta. Now, a third part of the question says that the operator failed to note the rise time. He didn't measure the rise time, so he wants to calculate the rise time. Predict the rise time, calculate the rise time based on the results of A and B. Results A and B, from the results we were able to come up with the transfer function of the process. So now I know the transfer function of the process. So the question now is, if we know the transfer function of the process, can we find the rise time? The answer simply is yes, because if I solve the transfer function, which is an underdamped system, and set the y to km and solve the equation, then the resulting time will be the rise time. Let me demonstrate this graphically. So again, I will draw the dynamics of the process. Let us change the color. Okay. So I have something like this. This is an underdamped system. Okay. Now, this is the steady state value, which is Km. Okay. The rise time, it is this. This is the TR, which is the time the curve first hits or crosses the steady state. So that means if I know this y of t, this is y of t, and substitute the value of Km, because at this point its value is Km in it, the resulting time will be the TR. So this is exactly what we are doing here. substituting Km for y and using the previous equation. This will be using the solution that were represented previously for the underdamped case. Here, there was a Km here and a Km here, so they will drop, and then we will have 0 for the y. Do you remember? There was a Km and 1 plus something. So when I bring it to the other side, it will be negative Km, and it will cancel with this. It becomes 0, and then the right-hand side will contain those two periodic functions. Now we need to solve this equation. This is known. This is known. So everything is known. The only unknown is the TR. This is a highly nonlinear equation and cannot be solved easily analytically. So the best way is to solve it numerically. One way to do this, we can use MATLAB to solve it, or we can use the numerical techniques that we have studied before. You can use the Newton-Raphson, the regular falsi, the false position, or the bisection method, secant method, different methods. We can use it to solve for TR. But if you have access to MATLAB, then you need to define the TR1, which is the value of TR, define the values of Z and tau, and then put the equation for the function, this function. And then the value of TR will be found by using the solve command. We write it this way: solve between brackets f, which is this function, f is equal to 0, comma TR1, and then this double is used to convert from symbolic to numeric value. This will give us the value of zeta of tau r as 694 seconds. So we were able to find the value of TR, the rise time, from the transfer function solution, and knowing the values of zeta and tau. This is this example, and this example demonstrates for you that if we have some practical data of the dynamics of the process, we can come up with the model for the process, and then we can use this model for describing the characteristics of its dynamics.